Here we have an example of a spring mounted horizontally, with its left end held stationary. By attaching a spring balance to the free end. If we pull the right end with a force 6.0 newtons causes a displacement of 0.03 meters. Then, we remove the spring balance and attach a 0.50 kilograms body to the end, pulling it to a distance of 0.020 meters, releasing it and watching it oscillate. Letter A, find the force constant of the spring balance when x equals 0.03 meters. And letter B, find A angular frequency, and period as the mass oscillates. First step, we draw the problem. So we have two cases. The first one is not oscillating but rather stationary but pulled by a spring balance, and second is that we allow it to oscillate with a mass attached to one end of the spring. The second step is to use the ideal equations. For letter A, we recall the expression for the restoring force, which is just force equals negative spring constant time displacement. We then substitute the known values of the force F equals to -6 newtons and positive x equals to 0.03 meters. The displacement x and F have opposite signs as mentioned earlier. Then we get a value of the spring constant of 200 newtons. For letter B, we find the angular frequency, and period. We recall the expression of angular frequency, which is equal to the square root of the ratio k over m. We get that the angular frequency is equal to 20 radians per second. For the frequency, it is equal to the angular frequency over 2 pi. We see that it is about 3.2 Hz a, and for the period, which is just the inversely proportional to frequency, we get t is about 0.31 seconds.